Okay, everyone. Hello and assalamu alaikum. Let's begin. We are starting our next topic today. We're done with forces in equilibrium and kinematics. Those were the big topics of mechanics, the two big topics of mechanics. You mostly get two questions on each of them. You get two questions on kinematics and two questions normally on forces in equilibrium. Those were the two bigger topics. Now we have three relatively smaller topics left. Uh, Newton's second law of motion has just one single concept, and momentum also has just one single concept. Work, energy, power will take a few days uh, in terms of its practice. Uh, but otherwise, we don't have a lot left now as far as the syllabus is concerned. The number of topics is three, yes, but it's not as time taking as forces in equilibrium and kinematics were. Okay, so let's start with this next topic. We will complete the concepts of this topic today. And then in the next couple of classes, we will be doing practice questions on this because it does require practice. Okay, so we will be spending time on practice questions on this particular topic because now all those problems that you skipped from the friction worksheet and from the kinematics worksheet, once we understand this concept, you should be able to do all of those questions after this. All right. So after today, if you have any problems in any friction question, any question from the friction worksheet, any question from the kinematics worksheet, or from any recent papers that do not involve work, energy, power, or momentum, you should be able to do those problems. Okay. So we will be spending a few minutes, sometime 15-20 minutes towards the end of this class in practice on a couple of practice questions. And then the next two classes, most likely, on more questions from the worksheet and otherwise, if you have problems in any question. Okay. So let's start with this. So the topic name is Newton's laws of motion, but practically there's only one law that we will be doing in this topic, and that's Newton's second law of motion. Now let's talk about this law and see what this says. So we've done two topics before this already. We're done with forces and we're done with kinematics. Newton's second law of motion is basically something that connects those two topics, right? So you'll find problems where in some part they will be talking about some forces, and in another part they'll be talking about quantities related to kinematics, for example, acceleration, displacement, time, velocity, things like that. So you might have acceleration of something given, and you might be asked to find some force. You might have velocity at some point given and displacement given, and you might be required to find some unknown force. So how do you connect forces and kinematics? That is where this Newton's second law of motion comes in. Now let's try to understand this using a very simple example. Let's say we have a surface here like this. And on the surface, we have some block placed. Okay, like this. There's a block that is lying on this plane. And you apply some force on this block, let's say towards the right side. Let's call this force P. Now this force P, let's say, has a magnitude of 15 Newton. Okay. Let's say it's a rough surface. So there's going to be friction as well. Friction is going to be at its maximum value, of course. Let's say that value is, in this case, 10 Newton. These are the forces that are acting along the surface. All right. There will be vertical forces as well. There will be weight of the object. There will be normal reaction, but they're not in the direction of motion. We're just ignoring them for now. They exist, yes. There's going to be reaction. There's going to be weight. We're not talking about that right now. We're just considering the forces acting along the plane. So we have 15 Newton acting towards the right side. We have 10 Newton acting towards the left side. What is going to happen? the object is going to start moving, right? Because there's some resultant force. What's that resultant force? Let's find the resultant force in this. The resultant force is 15 minus 10. That's 5 Newton towards the right side. That is the resultant force, right? 5 Newton towards the right side. Okay. Now, because of this resultant force, this object is going to start moving. It's going to start moving towards the right side because there's a net force acting towards the right side, right? So the object is going to start moving. Now, if the object is going to start moving, we want to understand how much distance is it going to travel, how much time is it going to take from one point to another, what is going to be the acceleration of this block, right? Things like this. We want to talk about all of those different things. What will be its velocity after some time? Now, for that, we have a relationship between resultant force and acceleration. And what does that look like? Think about it. If the result, what about the acceleration of this block? So if we were to connect acceleration, if we were to think about acceleration, the higher the resultant force is going to be, greater is going to be the acceleration. So if resultant force is more, if the resultant force value is high, the acceleration at which the object is going to start moving, that's also going to be high, right? So acceleration is going to be directly proportional to the force that is acting, the resultant force that's acting. And at the same time, if this object was, let's say, 10 kilograms as opposed to 1000 kilograms, which of those two is going to have more acceleration? The object that is lighter, that has less mass, is going to be easier to accelerate, right? It's going to have more acceleration. And the object that has a greater mass, that is going to be harder to move. This one is going to be harder to move, and its acceleration is going to be relatively lower. So acceleration is inversely proportional to 1 over m, or inversely proportional to m, right? So the acceleration of this block is actually directly proportional to resultant force and inversely proportional to m. And we basically have an equation that connects these three things now: acceleration, resultant force, and mass. The proportionality constant, it turns out, both of them is the same. So acceleration is equal to resultant force over m. If we rearrange this, we get something like this: resultant force equals mass into acceleration. And that is called the Newton's second law of motion. That if there is some resultant force acting on an object, the acceleration of that object is going to be that resultant force divided by mass, or in other words, resultant force is equal to mass into acceleration. Now, you would have often seen it written like this, and that's perfectly okay. F equals ma. But just to make sure that you understand what force we are talking about, the force that we're talking about in this equation is the resultant force. It's not just any force, it's resultant force. This force is not this 15 Newton. It's the resultant that you get after subtracting 10 from 15. Okay? So we're not going to be using 15 in that equation. We're going to be using 15 minus 10, which is the resultant force. So I would normally prefer writing this Newton's second law of motion as resultant force equals mass into acceleration, because that will help us avoid careless errors, because we would remember that we're talking about resultant force there. That's one way of writing this down. Another way of writing the same Newton's second law of motion down is, we could say, it's the forward force minus the backward force, or forward forces minus the backward forces, because there could be multiple forces as well. that equals mass into acceleration, right? That's what the resultant force is. So you subtract the backward forces, in this case that was friction, from the forward forces, from 15, and that gives you the resultant force. What is a forward force? You can actually write it down. Forward forces are basically, this basically stands for forward forces. These are forces acting in the direction of motion. This means backward forces, and that means forces acting opposite to the direction of motion. So this could be another way of writing this Newton's second law of motion. Now you need to remember this. Resultant force equals mass into acceleration. That is what you can use when you have an object on which some forces are applying and you want to find acceleration, or you have acceleration given and you want to find some missing force. This is what you can use. All right. I hope that makes sense. Now let's use this on this example that we had here. Let me just copy this. Let's say we had that block now. And there was a force acting towards the right side, that was 15. There was a force acting towards the left side, which was 10. We want to find the acceleration of this block due to this resultant force. Let's say the mass of this object is 3 kilograms. How would you find the acceleration? You would say resultant force equals mass into acceleration. That means the forward force minus the backward force. What's the forward force? The forward force is 15. Backward force is 10. Mass is 3 into A. That is what we have to find out. 5 over 3. That will give you 1.66666. That's 1.67 meters per second square. That's the acceleration of this block due to this resultant force. Okay. And now, given this, what you can do is you can find. So if you have acceleration, you know the initial velocity. Let's say this object started from rest. Let's say you want to find the distance traveled in 10 seconds. You could do that using the constant acceleration formulas. Acceleration here is going to be constant. Why? Because the forces are constant. This force is constant. This force is constant. Remember, we discussed this in kinematics. You need to remember that. In constant acceleration, we basically said whenever all the forces acting on an object are constant, acceleration is also constant. That means you can use the constant acceleration formulas. So in this case, let's say if in this case u was equal to 0 and time was 10 and acceleration is 1.67 as we have calculated here, we wanted to find the displacement in 10 seconds. How much has the object moved in 10 seconds? How would you find that? Which equation connects these four things? We could use S equals ut plus half at squared. Why? Again, because the acceleration is constant. All forces are constant. That's why acceleration is constant. So we can use the constant acceleration formulas. And we could find those unknowns. We could say the displacement is 0 times t, which is 10 plus half into a, which is 1.67 or 1.66666. Let's use more accuracy into t squared. That means 10 squared. And that will give you some value for displacement. That this is the distance or displacement that this object has covered in 10 seconds. What do you get from this? 83.5. So we get 83.5 meters.
83.35.
0.35.
Yes, sir.
83.35 meters. That's the displacement that we have in this case. So this object would have traveled 83.35 meters in 10 seconds. Okay. Now, I think Marino is getting 83.5. The reason for that might be you might have used 1.67 here. So if you use more accuracy, 1.6667, it might actually be closer to this. But that's okay. This is the result that we get. Okay. So that's the concept of Newton's second law of motion. Now, this was a very simple example in that you only had one object and that object had some forces applying, and you just use that rule directly like this. Now, a lot of times what would happen would be you'd have two objects connected to each other, and that is the more common scenario, that you'll have two objects which would be connected to each other. Now, let's take an example on that. Let's say we have a table like this, and on this table you have some block placed like this, and at the edge of this table, let's say you have a pulley or a peg. It's the same for us. You have this pulley, and let's say there is another object hanging below here, and these two objects are connected using a string. So there's a string passing over this pulley, and the two objects are connected using that string like this. So the string is passing over this pulley. That's going like this, and the object is hanging on the other side. All right. This is what the situation looks like. Now, assuming it's a smooth surface, that means there's no friction. So we're saying it's a smooth surface. What we want to do is we want to find the tension in the string. So we have two objects, right? So let me actually label them first. Let's say this is object A, this is object B. Now, since it's a smooth surface, there's no friction. That means due to the weight of this block, this block B is going to start moving downwards, and because of that, A is going to start moving towards right? So we want to find the acceleration of these blocks when they start moving and also the tension in the string. Now, let's assume that the weight of this or the masses of these blocks are given like this. Let's say the mass of A is 2 kilograms and mass of B is, let's say, 3 kilograms. What are the forces acting on these objects? Let me actually write down the statement here as well first. What we want to do is we want to find the tension in the string and the acceleration at which the objects start moving when released from rest. So let's say you were holding one of these objects. Let's say you were holding A at rest, right? So you're holding A at rest here, and then you release the system. What will happen? B will start moving downwards and A will start moving towards the right. You want to find the tension in the string while this happens, and also the acceleration in the string because of that. Acceleration of the objects because of that. Now, let's represent the forces acting on these objects. What are the forces acting on the object A? The weight of the object. That's going to be, if the mass is 2 kilograms, the weight of A is going to be 20 Newton. What about the reaction? The reaction is also going to be 20 Newton here because there's no other force. What else? We have tension that will be acting towards the right side. These are the forces acting on the object A. What about object B? Object B has tension acting upwards and it has weight acting downwards. What's the weight of B? That's 30 Newton. These are the forces acting on the object B. What we want to do is we want to find the tension in the string and the acceleration at which the objects start moving when released from rest. Now, how do you find that? Now, in such problems, what you're going to do is you're going to apply Newton's second law of motion on both the objects separately. Now, in physics, some of you might have used equations for the whole system. I would recommend that you don't do that generally unless there's no other possibility. Sometimes it happens that you have to use a whole system that simplifies things, but that's very, very rare. Mostly, what you would do is you would make two separate equations, and that's going to be easier to solve. Using the whole system very frequently results in careless errors with positive and negative signs, because when you're considering the whole system together, there's a very high chance of doing plus minus errors in that, because it's not clear a lot of times which side you should consider positive, which side you should consider negative, and if you're considering one side positive, how to assign positive and negative signs to the different forces that are acting, because in this case, some forces are horizontal, some are vertical. It becomes quite confusing. So I would recommend you apply Newton's second law of motion to each object separately. Do not use it for the whole system. That will confuse you in most cases. So let's look at this. What are the two objects that we have? We have two objects. One is object A and the other is object B. All we have to do is apply Newton's second law of motion on both the objects separately. You have this object A and you have this object B. All you have to do is use resultant force equals mass into acceleration. What are we looking for? We're looking for the tension in the string. That's a force, right? So that's going to be coming here. And we're looking for acceleration. And that's what we also have to find here. Now let's consider A first of all. Let's apply Newton's second law of motion on the object A first of all. Now A is going to be moving towards the right side. What's the forward force for A? The force in the direction of motion, that's tension. That's the forward force for A. So we say T minus the backward force. There's no backward force. That's a 0. Right? Because there's no force acting towards the left side. That equals mass of A, which is 2 kilograms, into acceleration. That gives us one equation, T equals 2 times A. Similarly, you apply Newton's second law of motion on the object B. In which direction is B moving? B is moving in the downward direction. What's the forward force for B? Forward force is 30 Newton, right? The force in the direction of motion, that is 30. Subtract from that the backward force. The backward force is T. That's 30 minus T. That equals mass of B, that's 3, into acceleration. Now, acceleration for both the objects is going to be the same, of course. Why? Because the magnitude of acceleration is going to be the same. Because they're both connected by a string. So whatever is the acceleration of one, the other has to have the same acceleration. Otherwise, they would not be connected, right? If they're connected, they have to move at the same acceleration, same velocity. Only the direction could be different, but the magnitude has to be the same. So we just apply these two equations. We apply Newton's second law of motion on both of them individually, and we get these two equations from that. We have two unknowns, two equations. We can find the values of those unknowns now. Tension and acceleration, that's what we're looking for. What we can do is let's input T equals 2A here, and that gives us 3 minus 30 minus 2 times A, that equals 3A, and that gives us 5A equals 30. The value of acceleration turns out to be 6 meters per second square. Now I put this back in the other equation, and that gives you T equals 2 into 6, and the value of tension turns out to be 12 Newton. All right. And that's it. That's what we were looking for. We were looking for the value of tension and acceleration, and we have found those two values. All right.
Yes, sir.
And that's it. That's all that we need to know about this topic. Everything else we are going to be using from the previous topics. Now, these are the basic concepts. Now, of course, when you look at questions, you will find that you will have complications there, because this is going to come in combination with kinematics and forces. So it's going to be 3 topics combined. So the questions that you get in this are sometimes complicated. So the rest of today's session, we will try and do a couple of questions quickly, and then we will do more practice tomorrow and maybe the day after tomorrow as well. All right, so we need to do more practice questions now. In terms of concepts, this is all that we have. So we have Newton's second law of motion. Resultant force equals mass into acceleration. Forward force minus the backward force, that equals mass into acceleration. If you have multiple objects, all you have to do is apply Newton's second law of motion on both of those objects one by one. Apply that separately on both of them, and that will give you the unknowns that you're looking for. Is that okay?
Yes, sir.
So now we can look at some questions from the worksheet. Let's start with a simple one, and then you can let me know, those of you who have attempted any questions already. So there are not many of you here in class today, but those of you who are here, can you raise your hand if you're doing A-level physics as well? Raise your hand if you're doing A-level physics as well. None of you? Okay, all right. So that means you had not done this law before. So maybe I could not expect you to have attempted any questions already, but in case you have attempted any questions and you have any problems already, you can also let me know about them. Otherwise, you can start working on the questions today. We will spend tomorrow's class definitely, and most of the Friday class, if not all, on more practice questions on this topic as well. All right. But in terms of concepts, in terms of new concepts, that's pretty much all that we have. But now let's see some questions from the worksheet and see what other complications we might get in them. By the way, those of you who are doing paper 3, as in who are appearing for the P3 exam, this is a very good question in recent papers. 2023, June 2023, paper 3, variant 1. I haven't seen any question like this in previous papers. This is a good one to look at for your exam preparation. June 23, paper 3, variant 1. It just came in front because I was discussing this with another student today. Okay, so kinematics worksheet. No. Friction worksheet. Okay, I think I have not assigned questions from this worksheet yet as well, so I'll just do that right now before we start doing questions. So you remember to attempt questions after class. Otherwise, it will get delayed. Okay, so I have actually uploaded the assigned questions as well. Yeah, so I've done that. So you should start working on those questions. There are a couple of other questions as well apart from this that I'll be assigning to you separately. So these are questions assigned from the friction worksheet, right? The friction worksheet that we used in forces and equilibrium topic. From that worksheet, you have some questions assigned on Classroom, which are related to Newton's second law of motion. So you should be attempting these questions now in the next couple of for the next couple of classes. In addition to these questions, you should also attempt any remaining problems from the kinematics worksheet that you could not do until now, because there are some questions in the kinematics worksheet as well that involve Newton's second law of motion. So you can also attempt those questions now. So have a look at them as well. If you have any problems in those questions, we can also discuss them in the next couple of classes. Okay, now for now, let's look at just one question. It's a relatively simpler one. Okay. Question number 11 from the worksheet. Let's try this. Okay, so it says particles P and Q of masses 0.6 kg and 0.2 kg respectively are attached to the ends of a light inextensible string, which passes over a fixed smooth peg. The particles are held at rest with the string taut. Okay, string taut, what does that mean? The string is straight. All right, the string is straight. There's no slack in the string. That means there is going to be tension in the string. All right. Both particles are at a height of 0.9 meters above the ground. The system is released and each of the particles moves vertically. Find the acceleration of P and the tension in the string before P reaches the ground. We need to find acceleration and the tension. This is the information that's given. So how do we think about this? Let me just highlight the important piece of information. We have the masses of P and Q. Yeah, so the rest of it is pretty obvious. We need to find acceleration and tension. Now, when the system is released from rest, see the masses of the two objects. One is 0.6 kilograms and the other is 0.2 kilograms. So what's the weight of P? The weight of P is going to be 6 Newton, that's acting downwards, and the weight of Q is 2 Newton, that's also acting downwards. Now, the weight of P is more as compared to Q. That means P is going to start moving downwards and Q is going to start moving upwards, right? Now, how do we find the acceleration and the tension? What are the forces acting on the object P? Weight, that's acting downwards. What else? We have tension. Tension is going to be acting away from P. That means in the upwards direction. This is the direction of tension. What about Q? There's tension acting on Q as well. That's also acting in the upwards direction. These are the forces acting on P and Q. P is moving downwards and Q is moving upwards, right? All you have to do is apply Newton's second law of motion on each of those two particles one by one. Resultant force equals mass into acceleration. For P, what's the forward force? P is moving downwards, right? Q is moving upwards. So the forward force for P is 6 Newton. We say 6 minus the backward force, which is T. This equals mass of P, which is 0.6 times acceleration. Q is moving upwards. What's the forward force for Q? T. Backward force is 2. So we have T minus 2 equals 0.2 times acceleration. And now And now what we can do is we can find the values of T and A, right? These are two equations that we have. We can find the value of tension and acceleration from this. Let's solve these two equations now. In the first equation, we can have tension equal to 0.6 times A. I'm sorry, that's 6 minus 0.6 times A. From the second equation, we get tension equal to 2 plus 0.2 times. Okay. We can equate both of them now. And that gives us 6 minus 0.6A. That equals 2 plus 0.2A, which is 0.8A equal to 4. And the value of A turns out to be 4 over 0.8, which is going to be 5 meters per second squared. That's the acceleration that we were looking for. Now what we can do is we can put this acceleration back in any one of those two equations to find the corresponding value for tension. If you put this in the first one, that gives us 6 minus 0.6 times 5. 0.6 into 5, that's going to be 3. 6 minus 3. The value of tension turns out to be 3 Newton. And that's what we were looking for. We were looking for acceleration and tension. That's it. That's 5 marks. All right. That's all that you have. Generally, it's like 4 marks, but still that's a lot for just this much working. You just apply Newton's second law of motion on both the objects one by one to find tension and acceleration from that. Okay. So generally, whenever you're asked for a force and acceleration at the same time, you would be using Newton's second law of motion. All right. Okay.
Yes, sir.
Now, what's the second part? The second part says find the time taken for P to reach the ground. Now, P is moving downwards, Q is moving upwards. How much time does P take to reach the ground? We have displacement given, we know acceleration, right? So we have all the information given. P is moving downwards, remember? So which direction should we take positive for P? P is moving downwards. We say downwards is positive for that. What do we know about P? P started from rest, right? It says the particles are held at rest and then they're released from rest. So initial velocity is 0. We have found acceleration. Acceleration is 5. We know displacement. Displacement until the object reaches ground is 0.9 meters. That's the value of displacement. What are we looking for? We are looking for the time taken, right? S, U, A, and T, which equation connects these 4 things? S equals UT plus half AT squared. Just input values in this, and that gives you 0.9 equals 0 times T plus half into A, which is 5 into T squared. And that will give you the value of T, 0.9 into 2, that's going to be 1.8. 1.8 equals 5T squared. T squared equals 1.8 over 5, and then square root of that. What's the value of T that we get? What's the value of T?
So 3 over 5.
3 over 5.
So 0.6.
0.6. That's the time taken for the particle P to hit the ground. And that's all that we were looking for. Make sense?
Yes, sir.
Okay. Okay, I hope that makes sense. Let's have a look at one more question before we end. I'll just show you this question. I'll be back in a minute. I need to just take care of something. Let's have a look at one more question. And then you'll attempt more questions from the worksheet. We will discuss the problems that you have in tomorrow's class then, inshallah. This is one particular question that I definitely want all of you to try. Question number 2, and along with this 26 as well. Let me see if I can find the question that I want to discuss now. Let's look at this one. For tomorrow, by the way, please note these questions down that you need to do at a minimum. Question number 22 from the worksheet. I'm actually going to write it down. Can somebody please post them in the group as well? I'm just writing them in the chat box. 22. And then you have 52. And this is the good one, 67. Fifty-one to 26. Yeah. So these six questions, question number 2, 22, 26, 51, 52, 67. These are questions that I definitely want you to try for tomorrow's class. Let me know if you have any problems in any of them. We want to discuss them tomorrow. Now let's just end with this one question for today. Question number 8 from the worksheet. Let's try this and then we end. Now, it's also a relatively complicated one. Let's have a look at this. So I'll leave you on this. Leave this on the screen. Try this. I'll be back in a minute.
It's me.
Okay, let's assume my iPad is also running out of battery. So hopefully we can complete this. If not, we will continue with this tomorrow. Let's quickly try this. Two particles P and Q move on a line of greater slope of a smooth inclined plane. The particles start at the same instant and from the same point, each with speed 1.3 meters per second. So there's a smooth inclined plane. Whenever you don't have a diagram given, it's always helpful to sketch a rough diagram. So we have an inclined plane. It's a smooth plane. That means there's no friction. So it looks like this. Now there are two particles P and Q. They start from the same point. So there's some point here. Let's say this is where they start from. Each with speed 1.3 meters per second. Initially, P moves down the plane and Q moves up the plane. So P is moving down the plane at 1.3 meters per second, and Q is moving up the plane. Both of them start at 1.3 meters per second. Okay, these are the two objects that we have, P and Q. The distance between the particles t seconds after they start to move is d meters. Distance between the particles t seconds after they start moving is 1.6 meters. We need to find, I'm sorry, I read something else there. The distance between particles t seconds start to move is d meters. Show that d equals 2.6 times d. That's what we need to show in the first part. That's 4 marks. Distance between the particles t seconds after they start to move. Now let's think about this. It's a smooth inclined surface. It's a smooth inclined surface. And there are no forces acting apart from the weights of the object. Does that remind you of something? Can we say anything about acceleration? Can we say anything about the acceleration of the objects?
Sure, the acceleration will be constant. It will be
Acceleration will
zero.
be constant?
It will be zero. It will be zero. Because it's
Acceleration will be
the
zero?
same. Because they have the same speed.
They have the same speed, yes. But how is acceleration zero? Is the acceleration changing or not changing? How do we know that? Do we know if acceleration is changing or not?
No, sir.
How do we know if acceleration is changing? Acceleration changes if the forces acting on the object changes, right? Here, the forces acting on the objects, they're not changing. So acceleration is going to be constant. It's a smooth surface. Weight is the only force acting. In fact, in this case, they haven't really specified if there's another force or not. Let's just think about that. Okay, so what we can do is, we have, in fact, all the information that we need here. P is moving downwards and Q is moving upwards. That's how they're starting. P is moving downwards. If we consider the downward direction is positive for P and the upward direction is positive for Q, we actually have pretty much everything that we need, because P is here and Q is here. P is moving down the plane and Q is moving up the plane. So if you think about P, its initial velocity is 1.3 meters per second. And Q's initial velocity is also 1.3 meters per second. For both of them, since we're considering different directions positive, for P, we're considering down the plane positive. For Q, we're considering up the plane positive. Their velocities are going to be positive in those directions, right? So both of them have 1.3 velocity. Now, whatever is the acceleration of particle P that is moving down the plane, what about the acceleration of the other particle? The acceleration of the other particle is going to be negative of that. Does that make sense? Since the acceleration is going to be acting down the plane, the acceleration is going to be acting down the plane. If we consider the acceleration at P to be positive, for Q, it would be negative. So let's say acceleration was AP for, or let me actually add it like this, in fact. If acceleration of P was A, what about acceleration of Q? That would be considered as negative. Okay. So basically what I was referring to earlier was, since the acceleration is, since there's no force acting apart from weight of the objects, the acceleration is going to be constant on the surface. Why? Because it's a smooth inclined surface. It's a smooth inclined surface. Weight is the only force. Remember what acceleration used to be in this case? We've done this before. Acceleration used to be 10 sine theta. So we did this here when we did motion under gravity. Smooth inclined surface with weight as the only force, acceleration used to be 10 sine theta. Now, if we had the angle of inclination of the plane known, we could write down the acceleration as 10 sine theta. But here the problem is we don't know what the angle is going to be, right? And they have not given us the angle. If we had the angle given, we could find that acceleration. But what we can still say is, whatever is the acceleration of P down the plane, because down the plane, acceleration of P would be 10 sine theta, whatever that angle is. Then acceleration of Q would be minus 10 sine theta, because for Q, we are taking up the plane positive. And acceleration is acting down the plane. So that's going to be minus 10 sine theta, or we can say minus A. That's the acceleration of Q. So if acceleration of P is A, the acceleration of Q is going to be negative A. What else do we need? We have time. Time is common between them. It says the distance between the particles t seconds after they move. That's what they're talking about. They started from the same instant. After t seconds have passed, what is the time of both the particles? The time of both the particles is also going to be the same. So if the first one is t, the other one is also t. So time is common. That's the other variable that we consider. And we are given that the distance between the particles after t seconds is d meters. Distance between the particles after t seconds is given by d meters. So if the displacement of particle P was SP, and the displacement of particle Q was, let's say, SQ, displacement of Q, what would be the distance between the particles? Think about it. If P moves like this and Q moves like this is SP and SQ. This is the distance between the two particles until that point. The distance between the two particles will be the sum of these two values, SP plus SQ. That will be the distance between the two particles. Does that make sense? And now you can just evaluate this and see what this turns out to be. You have these four quantities, U, A, T, and S. SP would be ut plus half at squared, that's 1.3 times t, plus half into a into t squared. plus SQ, that's 1.3 into T plus half into A, but now A is negative A, times T squared. Simplify this, and that gives you 1.3T plus 1 over 2AT squared plus 1.3T minus 1 over 2AT squared. These terms get cancelled out, and we're just left with 2.6 times T. And that is what we had to prove there, that the distance between the particles is given by 2.6 times T. Does that make sense?
Yes, sir.
All right, that's what we had to prove in the first part. D equals 1.6 times T, 2.6 times T. So P is moving downwards, we consider that direction positive for P. Q is moving upwards, we consider that direction positive for Q. We have all the information given that we need. Initial velocities, acceleration of one is A, the other is negative A, time is common. The sum of displacements should be equal to D, and we found D to be equal to 2.6T now. Now it says when T equals 2.5, the difference in the vertical height of the particles is 1.6. Find the acceleration of the particles down the plane. Okay, part 2. Now what they're saying is, when T equals 2.5, the difference in the vertical height is 1.6 meters. Now this is the plane. At some point, P is here because P was moving downwards and Q was moving upward. Let's say Q is here. The difference between their vertical heights, that means this distance. What's this? This distance is 1.6 meters. At what point? At T equals 2.5. Can we find the distance between the particles at this point? We have this relationship now. D equals 2.6 times T. We can just input the value of T in this, and that gives us 2.6 into 2.5. What's that? 5.2 and 6.5, right? 6.5 meters. That's going to be D. That means that this distance between the particles is 6.5. What are we looking for? We are looking for the acceleration of the particles. Remember what acceleration of the particles here is going to be? 10 sine theta. We discussed that before as well. If we can find the angle theta here, we can find the acceleration, right? How do you find the angle theta now? You've got the hypotenuse, you've got the vertical height, you've got both of those things. You can find this angle. Let's call this angle theta. This is the angle of inclination of the plane. You can say tan theta equals 1.6 over 6.5. That will give you a value of theta. And then you can just input that in 10 sine theta. What's the value of theta that we get? What's theta?
13.83.
13.83. We put that here, 13.83 degrees. And that will give us the value of acceleration. You can see what this turns out to be.
2.39.
2.39?
Yes, sir.
2.39 meters per second square. That's the acceleration that we were looking for. Okay. All right. That's the second part. Now let's look at the third part. Do that quickly. It says distance traveled by P when Q is at its highest point. Okay. So what's the distance traveled by P when Q is at its highest point? Now, when Q is at its highest point, what is the velocity of Q at that point? Just like in vertical motion, at the highest point, velocity is 0. Here as well, Q is going to move. What's the journey of Q going to be like? It's going to move upwards, and then at some point it's going to come down. At the highest point, its velocity is going to be 0. So what we can do is we can find the time taken for Q to reach its maximum height, and then use that same time for P to figure out how much distance it has traveled down the plane in that time, right? So let's do that quickly. So basically, what I mean is, part 3, Q is moving up the plane. That's going like this. What do we know about Q? We know initial velocity, that was 1.3. We know acceleration now. Acceleration is minus 2.39. Remember, acceleration is acting downward for Q. What else? We know the final velocity, that is 0. We also know the initial velocity. What else? Displacement is not known. Time is what we can find now, because that time then we can use for P, because we want to find the distance traveled by P when Q is at its highest point. So we can find the time taken by Q to reach its highest point, reach the highest point. Let's see what that turns out to be. We can use this equation, V equals U plus AT. 0 equals 1.3 minus 2.39 multiplied by T. What's the value of T that we get?
Zero 0.544.
0.544. We want more accuracy in working so that our final answer is accurate. .54.
Sir, it would be then 0.54393.
0.54393. So let's say 5. Okay, so I'm sorry, I lost connection on the other device because my iPad's battery is finished now. So basically what happens is you found the time taken for Q now to reach its maximum point, right? Once you have found that maximum point, the time taken to reach the maximum point, you know the initial velocity for P, you know the acceleration of P, that's going to be positive because that's acting down the plane, right? That acceleration is going to be positive. What else? Okay, I'm sorry. I was just looking at this working again, and the angle that we've calculated is wrong. We have used tan here instead of sine because there was perpendicular and hypotenuse, right? So in a hurry, I think I made that mistake. So look at the working that we did earlier. I used tan there instead of sine, right? So the angle is inaccurate. So we will correct that angle first. Use sine theta equals 1.6 over 6.5. Then you would use that to find acceleration in the previous part. And then in the next part, you would basically use the same method that we have done before to find the time taken for Q to reach the maximum height. Then use that time taken to figure out the distance traveled by P down the plane. Okay, remind me in the next class, I'll correct this. Where it'll actually take time for me to turn my iPad on now. It will take a few minutes. So we'll end this class here for now. Do you understand the question? Will you be able to do that now?
Yes, sir.
Right? Okay, so try that. We will, in the first few minutes, try to complete this question. The next class, please try to attempt the assigned questions from the worksheet as well. We will be looking at some of those questions in tomorrow's class. And then on Friday, we will spend the last session on this because that's pretty much all that we have in this topic. On Saturday, then we can start the next one, which is work, energy, and power, inshallah. All right, I'll see you again on Wednesday. That's tomorrow, in fact. Allah Hafiz. Bye.